Hey everybody, what we're going to do in this video is cover how to do a repeated measures one-way ANOVA using JASP, Excel, GPower, maybe a couple of other programs. With the last video I realized I didn't explain very well what the example was about, so this time I remember to do that. And what we're looking at is a repeated measures design, so that means that each person is used multiple times. The advantage to repeated measures designs is that they have more power, so less people needed for the same level of detection, and so you get more bang for your buck. The problem with repeated measures designs is they're a bit more complicated to analyze because you have to deal with the fact that the people are the same people several times, which is sometimes called correlated error, where each person has their own personness, if you will. Additionally, you have to deal with some issues with research design, such as fatigue, carryover effects, counterbalancing. So just by being the first thing that they do, that might inherently be different than if it's the last thing that they do. And so this silly example, what we have is people tested over several different days, and we're measuring their pulse given different types of stimuli that we're going to show them. So one day they see a neutral picture like a toaster, while other times they might see like pictures of puppies, and then the negative stimuli are things like mutilated faces, so they cause a big shock value. So are there differences in pulse for each participant? Okay, this is made up data, so the pulse values might be kind of high, like your heart might explode at some of these ranges, but let's just pretend to make this work. But in reality, with this kind of data, when you understand the min and max a little better, you might be able to say, I bet the equipment was malfunctioning because their pulse probably wasn't 10 beats per minute, or their pulse probably wasn't 300 beats per minute because your heart would explode. So just kind of a warning that a lot of the examples that I have are totally made up data, and so it can be sometimes difficult to make sure they're appropriately scaled without going into too much work. Either way, let us start by running the analysis. So I have power and the results in here already, but we're going to kind of work through the same order we did in the last video. We're talking about data screening and then the analysis. And I'll add some more notes to this document and upload this on Blackboard for you guys. Okay. So here's our data set we're going to start with. So remember, I'm going to save the CSV as an Excel document just so I can work with it a little more. So data screening, great. So this is our master data set. So one thing we might want to do is create our no typos data set or edited data set in some way so we don't screw up our master data set. I'm going to paste that in here. So what I've got are 3 columns, one for each of the levels of the IV. So the biggest trouble sometimes people have in understanding repeated measures data, the actual data, is the difference between the IV and the DV. So the IV is the names of the columns. Those are the levels of the IV. So we've shown them neutral, positive, and negative pictures. The DV itself here is pulse. So these ranges of heart rate, if you will. And I think I maybe toned them down a bit from what they were before, but obviously this 201 is kind of high. With the IV and the DV separation here, with between subjects designs, it's really easy. We've got group in one column and DV in the other. So IV in one column, DV in the other. But with repeated measures, we're doing this in wide format, which means that each person has their own row. So I think about this as like unique snowflakes. So each person is their own unique snowflake, which means they should get their own row. And since each person has data in each row, we'll have to check a couple of different little assumption things that we didn't do for repeated measures. Okay. So let's just go ahead and get started. Let's work on data screening. So as part of data screening, first thing we're going to do is check for accuracy, with the caveat that we know that some of these scores are probably too high. Okay. So to do that, I'm going to click Data, Data Analysis. I'm going to pick Descriptive Statistics. In this particular case, I'm going to use all 3 rows because I don't have any categorical columns, so there are no labels to check in this one. Labels in the first row, summary stats. Click OK. I'm going to rename this one accuracy, blow it up a little bit. So I'm really concerned with, here, click, looking at our min and max here for accuracy. So I'd probably say that some of these are a little too high and I might need to fix them, but let's pretend that all these numbers are valid, but this is how I would check. Something I didn't cover in the last video is you can also look here at skew and kurtosis because we weren't totally sure about normality because of the charts and how they were looking. So my skew and kurtosis values here are not very scary, right? Remember 3 outside of 3 is when they get too large. So for right now though, for accuracy's sake, I'm interested in these values. So I don't have any negative scores, so that's good. And I don't have any scores like 99,000, so that's also good. So I would say we were doing all right for accuracy. I can also look here and see I have the same count for each one. And here I don't seem to have any missing data. But if we were interested in doing it like we had in the very first video, so we do equals, count A, highlight all of your scores, right, divided by the number of scores. We've got 18 scores times 100. Right. And that would give me the percent valid for each one. We wouldn't want anything to be below 95%. But this is a small data set, so I know that everything is okay. Oops, I hit the wrong button. Okay, so I also don't have any missing data, so that's really great. 2 easy things to deal with. Now, outliers here is a bit of a trickier story. So let's create a no outliers data set. Oh, good grief, Excel. I have the worst trouble with Excel lately. Okay, you gonna open back up? Yep. So this is why you hit save and save often. All right. Let's hit the plus sign here. Let's create a no missing or no outliers data set. And let's just see if we have any outliers. So to do that, I'm gonna copy this. I'm gonna paste it over here. Now there's 2 ways to handle this. Because I only have 3 columns, I could create z-scores for each column, or like in the first data screening video, I could create an average score and look at the z-scores for the average. The z-scores for an average makes sense if we're talking about scales, meaning like I'm going to use the total score for that scale anyway, so I have each individual question, and then I can create a total score that I'm going to use in my analysis. And so that would be when I would suggest doing that, because that makes it a little easier to data screen as well, because I'm only dealing with 1 column instead of maybe 25 questions or 40 questions. In this situation, because I'm expecting differences between levels, right? So between each one of these testing times, let's try outliers 1 column at a time. So this is going to be z neutral, z positive, and z negative. So to do that, we're going to do the formula. So equals, open parentheses, click on the first column in neutral here, or the first cell in neutral. So that's x minus the average for this column. So type the word average, open parentheses, click on the whole column, close parentheses, close one more time, divided by STDEV, open parentheses, and that column again. So remember, this is x minus the mean divided by the standard deviation. I'm gonna hit enter. Remember, I can change that to be the little, like, from the white arrow to the black one here, and I'm gonna double click. Okay. Now watch this. This is the coolest part. I can, I'm fairly sure, hopefully, drag this way to get the z-scores for each of the other columns. So if I highlight this, what I see is that it's moved all the cells 1 to the right. So Excel sometimes has this cool feature where it will autofill what it thinks the formula should be in other columns. Sometimes that's good, sometimes that's bad. In this situation, it's fantastic. So that auto-filled given column B. And then for the next one over, given column C. So it's only comparing C2 to the average for C and the standard deviation for C. So kind of a nice trick. The next thing you can do is highlight these 2 and click when it goes from white to being black, double click, and it will fill all of those in for you as well. So that's really awesome. And it allows me to get a better, to do this a lot faster. Now what I want to do is I want to sort, or I want to look for anything above or below -3. So we could sort, but sorting takes a little while. So what I'm going to do is just highlight them, and we actually did this trick for a different thing. But in the home window, so home, click conditional formatting, highlight cell rules, greater than, and just put 2.99. And that will highlight any cells that are greater than 2.99, so 3 and up. I'm going to do the same thing, highlight cell rules, less than -2.99, so I can get the bottom and the top. And nothing got highlighted. So none of these scores are outliers within their own level. So no person has a score that's an outlier within its own level, meaning for neutral, nobody's scores are outliers for positive or for negative. So I wouldn't need to exclude anyone. Now there are a couple of ways that you could exclude people. If, let's say, they have an outlier here on neutral, but not on these other two levels, then maybe I only exclude them for neutral. Or if, however, you exclude their neutral score, it will delete the whole row when you go to run the analysis. So if you exclude any one of these columns, it will, like if I say, let's say, just delete this data point, right? It will then exclude the whole row because of the way ANOVA works. So if you decide to exclude someone because they have an outlier on any one point, it will exclude the whole person. Or what you could do is see if they're an outlier on more than one. So if they're an outlier on just one column, maybe I'll leave them in. They were a little weird in that condition. But let's say they're an outlier on all 3 columns, that is suspicious. So I would exclude them. That's especially useful if you're dealing with data where they're like picking scores and people are just dicking around. They're picking like 1, 7, 1, 7. It's really annoying, that sort of thing. Okay, so I don't have any outliers, which is great because that means this data set is, unless I have some assumptions problem, the same data set that I started with. So let's create our final data set here, which is again the same one we started with. But now I'm going to use this final page to do the dirty work for assumptions testing. Okay. The first thing I want to test for is additivity. I do need to test for that for here, but here, warning, quiz question coming. I want to check to make sure that my additivity isn't perfect correlations. So the point of a repeated measures ANOVA is that we're using people multiple times. And therefore, usually, those columns will be correlated because it's the same persons being tested multiple times. So I know the rule for additivity normally is 0.9, where it becomes problematic. But here, what we want to do is just make sure no 2 columns are perfectly correlated, because a perfect correlation will screw up the math. Okay. So to do that, I'm going to click Data, Data Analysis, and then there's correlation on here. Click OK. We're just going to highlight everything here. Labels in the first row. Click OK. So I'm going to label that correlations down here. That's for additivity. I'll scroll up. Now last time we talked about how to highlight these, but this is kind of a small table, so I'm just going to look at them. Look how correlated they are. Okay, so they are correlated above 0.9, which would have normally set off a little alarm bells. But these are the same people, and we're testing their pulse across different days. And so my pulse is blah, blah, blah. 1, 2, 3, it's tied to my resting heart rate, right? And so I'm going to be the same person. I'm going to have this. If I start with low scores, I would expect me to still have lower scores than everyone else. So it having a really high correlation is somewhat expected. So what I would do here is just make sure they're not perfectly correlated. Remembering that these 3 will always be 1, because that's the correlation with itself. So those don't count. So I want to look here and just make sure that none of those are 1 as well. Because if they're perfectly correlated, it's not gonna mathematically run. You're gonna have problems. Okay. So we're okay. Remember that the rule for additivity for repeated measures is that it cannot be 1. Okay? It can correlate with itself. You know, that's just because it's correlating with its own column. But between neutral and positive here, it cannot be 1. The normal rule for additivity is 0.9. The rule for additivity in repeated measures is no perfect correlations. Okay, it's like 0.999. All right, all that being said, additivity is fine. Let's check our other assumptions. So I'm going to create my random variable. Okay, so equals rand, open close parentheses. Double click from the white plus to the black plus here. Get my random number. We're going to try this with 3 columns and see if Excel will play along. I have not tested this, so we're doing this on the fly, so fingers crossed. Click data, okay. Data analysis, regression, click OK. Our Y scores are the random scores. Our X scores are our 3 columns, ABC, all the way, I'm highlighting all of the data. I want my standardized residuals and my residual plots and my normal probability plots. So fingers crossed, fingers crossed. Sometimes it's grumpy. Yes! All right. Huzzah. So we're not going to look at any of this. So I'm just going to black it out, so I'm not tempted to look at it. Let's create a normality histogram. So I'm going to highlight my standardized residuals. I'm going to go up to data again, data analysis. This time we're going to go to histogram. My input range are these residuals. Output range, we're just going to stick that plot right here in the same sheet and give me the chart. And click OK. So my normality, now it does pick whatever bins it wants. So this is a little bit of the issue, is that it picks these bins, but we'll be able to look at, you know, the individual plots and look at this again in JASP just to kind of have some confirmation here. And it's okay. 0 is right here in the middle. And so it's a little negative skewed because I have more data over here on the positive side than the negative side. So a touch negative skewed. Do I have at least 30 people? No, actually. So I only have 19 people. So this would be better if I had at least 30 people. It's not terrible. It's not great. It's okay. Let's look at our normal probability plot here. Let's make it a little bigger. So I'm going to right click, add trend line. Okay. And that's pretty close. It will be able to look at a QQ plot in JASP, I believe. And so it actually goes through 0 here and is pretty close to the line. So I would say this is pretty good for linearity. Let's look at homoscedasticity and homogeneity. Now it does this by variable. So it would be better if we had a plot of all of the variables at once, but we can look at this by variable as well. I just don't have enough room. Let's scroll this way. So for, come on, our 3 variables here, let's see how this looks. Excel is like having a Monday. All right, there we go. So for the 3rd variable here, this is like perfect. It's evenly spread around 0. It's evenly spread through the middle. The spread, so for homogeneity. Homoscedasticity, the spread is pretty blobbish. This one's also pretty perfect from 4 to 4, pretty blobbish. So a couple more numbers at the top than the bottom. And for some reason, this one though, minus the fact that there's nothing here on the bottom, given that the bottom here is like, you know, elite runners and dead people, I would say this actually looks okay. So the range is from 8 to 0.6, which is pretty even spread, and it is sort of blobbish. So I'd say it's all right. But we can also get this particular chart for all of them together instead of each variable one at a time. What you want to do is click highlight. This is going to be kind of a pain, but we're going to copy all of this. And I'm going to scroll down here, paste it. I'm going to delete this one here. And we can actually look at a scatter plot of predicted y by standardized residuals. Okay. Predicted y, we should really z-score first, but that's like a little bit too much work. So we're just going to highlight these two, predicted y and standardized residuals. Click insert, and it's a scatter plot here. And we don't have to clean this chart up, we just got to make it. And we just want to see if I look at all of them combined, do I get a chart that sort of matches the other three charts. So I can look at each one individually here, or I can do all of them together. And I would say, you know, excluding the fact there's no data here. So Excel makes these graphs automatically, and so it almost always starts from 0. So I'm just going to kind of ignore the left side of the graph here. Is this spread even around 0? It's pretty even. Runs from 2 to 2, which is pretty predictable. And I would say it's fairly even spread if I could find the middle here. Does it make sort of a blob? So yeah, I'd say so. I could draw a circle around that and it would be fairly blobby. Okay, it's not perfect because there should be like another dot right here, but it's pretty good. The middle is missing a little as well. But overall, given that we're never too harsh on these graphs, I would say both of these look pretty good. We'll be able to confirm some of that data analysis, data screening stuff when we get to JASP. So all that taken together, I would say we don't have any typos, we don't have any accuracy issues, no missing, no outliers, and our assumptions look pretty good. Better if we had more people, but we're doing okay. So let's close this window and go back to JASP. Let's open our data set. Remember, it has to be a CSV, but I didn't change anything, so I can use my original one. Okay, so we're working with RM1 here. So I've got my 3 columns. I could change all of these to scale. It's not really going to mean a whole lot here, but they are all scale variables. I could look at the descriptives for each one. So move all 3 over here. And I could tell I don't have any missing data. I can look at my means, the standard deviation. So this should just confirm what we found in Excel. I could look at skew and kurtosis again. Right? I don't have any crazy values. But really, if I wasn't sure about normality, I could look at my distribution plots, remembering that it's okay if the sample isn't normal, it's the sampling distribution we care about, but maybe one of these is more skewed than the others. Okay? And these kind of all look okay, right? I can't really change the binning on the bottom, so they look a little like multimodal, but remembering that, you know, the range on the bottom is kind of squishing them to make them look that way. Okay. So I'd say these are all pretty good. They're actually mostly rectangular. So the distribution on these is actually pretty flat. All right, but the real magic is going to happen here, so I'm going to get rid of this because I don't really need it. Yes, is working on the actual ANOVA. So let's run that ANOVA and we'll talk about the data screening procedures that we get out of the ANOVA here. So click on repeated measures ANOVA. And this output looks a little different. So we can relabel the name of the factor here. So we're interested here in the IV name is stimuli. Or stimulus. You can go nuts either way. That first level is going to be our neutral level. Our second level is going to be positive here. And we're going to add a third level of negative. Okay. It starts off with 2 because you have to have at least 2, and you can add as many as you need. By doing that up here, now I know how to plug in my cells down here. So you can drag and drop. Oops, I did that wrong. You can just make sure they're in order, so neutral matched up to neutral, to positive here, to negative. So just make sure they line up in the way you expect. This allows you to add some really nice little labels. It automatically pops up my ANOVA over here. which is cool. So I'm going to scroll down. I'm going to add some extra stuff. So first, let's add this assumption check. And sporicity is our big one here. So sporicity is like, it's homogeneity with a twist. So sporicity is the assumption that the correlation between levels is equal. So positive to neutral, negative to neutral, all have the same correlation between them. And we've tested that in our Excel sheet. We had like 0.8, 0.9, and 0.9. So they're pretty equal. That's part of sporicity. The other part of sporicity is the variances part. But it's not quite that positive, negative, and neutral have equal variances, because that would be too easy. What it is instead is that the differences in variances are equal. So if I took positive and I subtracted negative, that difference score's variance would be the same as if I took positive and subtracted neutral and then calculated the difference score. So it's that the correlations between levels are the same and the the variances of the differences are the same. Okay. Sometimes that's called compound symmetry, but the big thing to get here is that sporicity is a sort of homogeneity test, but it's special for repeated measures. Now, it's called Mauchly's. Levine's test is for between subjects ANOVA. Mauchly's is for repeated measures ANOVA. And you can actually ask it to give you Levine's test, but it will tell me that, like, you really know you can't do that because I haven't asked for any between subjects. So I don't have anything here, so it won't allow me to put anything here. So I'm gonna turn that off. Okay. Now, this is Mauchly's. I'm sorry, this is a data screening test, and we're gonna go with the big important rule, remembering that that's 0.001. If you want to go with 0.05, like if you're a different researcher, if you're in my class, ignore me for a second, you could go with 0.05 and then I would tell you to correct here. But I always go with the assumption that we're going to make things really, really nuts before we change things. This is from Tabachnik and Fidel. And so I would say this is not significant, but damn, it's close. So jokingly, sometimes we've called this in my class the new kids on the block rule, although I really need to come up with a new example because that I'm showing my age. Where anytime you see output here that says "oh," so like the Right Stuff song, if you are a young person, you should Google it and then it'll be stuck in your head all day. Anytime you see "oh," which means it's less than 0.001, that's when you have to worry. Here, this is not significant, but let's talk about what do I do if it is significant. What you get out here on the side are two epsilons. That's a little e thing. Epsilon is a measure of the sporicity, and the big two options here are Greenhouse Geyser and Hunfeld. And what you do is if they're both over 0.75, then you use Hunfeld. If they're under 0.75, you use Greenhouse Geyser. If it's split, like one's under and one's over, take your pick. Generally, people will use Hunfeld. So Greenhouse Geyser is a little more restrictive. Hunfeld's a little bit more powerful. It's kind of like the difference between Tukey and Bonferroni. But in this particular instance, since they're both under 0.75, I would go with Greenhouse Geyser. What does that mean? I say I go with it. What do I do? What you do is you click sporicity corrections here to turn them on, and you'll see that you get a lot more output. And this, for SPSS users, should be much more familiar. You always see these. And then you would use the corrected line. So if I wanted to correct, I needed to correct because it was 0.000, I could say, okay, I'm going to pick Greenhouse Geyser because it's less than 0.75, and I would just use that entire line here. So it's going to look weird because it's going to be partial degrees of freedom. So the degrees of freedom are going to be decimals instead of whole numbers. And that's a little weird for people sometimes, but that is correct. Because what it does to correct, so we talked about Tukey last time and Bonferroni, those correct on alpha or the cutoff score. Okay. The way that Greenhouse Geyser and Hunfeld correct is on degrees of freedom. So it multiplies the original degrees of freedom times this epsilon. So 0.64 times 2 will give you this 1.28. Okay. And I actually never knew that in all the years that I had learned statistics until I read the Andy Field book, and it was like mind-blowing moment. Like, where the F did they get these degrees of freedom from? Until finally he was like, oh yeah, by the way, it's calculated by multiplying by these epsilon values. Not something you have to remember, but FYI, that's where those numbers magically are coming from. Okay. And so when a reviewer tells you that you're wrong because you have partial degrees of freedom, that is a good place to cite. Is maybe Annie Field's book or the Tabachnik book or shit. You can cite the video if you would like. That is not wrong. Those are correct. So the correction is on degrees of freedom, which then changes your p-value. Definitely know that you should report partial degrees of freedom and that reviewer is wrong. Personal experience. Okay, now here it doesn't give me the little warning that it's the assumption of sporicity is violated, but we're going to use a different criteria than this. Mostly because these tests are sensitive. And that would be good if we were wanting them to be, if we were wanting to use the same criterion, but we're mostly wanting to use very, very strict criterion before we edit data or manipulate it somehow. So we want the data to be what it is and not necessarily throw on corrections that aren't needed. But if someone says, yes, you should correct, that's how you would do it. All right, so covered data screening now. So I think you can also get some fun plots. Let's see what other plots. Well, we can add our effect size. So I can get eta squared out here. Look how big it is. It's almost perfect. So we got 94% of the variance, which is clear that it is made up data at that point, right? And we can also ask for our descriptive statistics. This is going to be really helpful for effect size. But actually for effect size, we're going to have a cheat on this one. But we're still going to ask for it. All right. Now we've run the analysis because we've been talking about it. So I've covered data screening completely. Let's look at this analysis. So if we're not correcting, I'm just going to scroll across here. This is significant any way we slice it actually, but it is less than 0.001. The criterion for hypothesis testing is 0.05, so it's definitely significant. Okay. And the effect size is very large. So what that implies is that there's a difference between these different pulses, but where? If I look at my descriptives, it's pretty clear to me that they're different, given a very large difference between neutral and positive, and neutral and negative. What I would like to know more precisely, is that a significant difference? And even better, is that a large difference? So we're going to calculate the effect sizes for these as well. Okay. So remember, an omnibus ANOVA, or the overall ANOVA, tells me that there is a difference between levels somewhere, and now I would like to know where. To do that, I'm going to click Posthoc Test. Move my stimuli over. Remember, you can pick Tukey or Bonferroni, but kind of like Tukey. And it gives me this nice pretty table that we saw in the Between Subjects ANOVA video with our corrected p-values. So they're all significantly different. Okay. Now please note this calculates the t-test based on standard error based on some calculations of residual mean squared error up here. So that's why they're all the same, which that means that if we were to calculate our effect size on these, it's not going to be based on these values here, but instead these descriptive values here. Okay, so we've covered our post hocs, so they're all significantly different. We're going to make the same table we made last time. And so really what I need now is to calculate the effect size for these. Now you could use MOTE, which I will open real quick. Oops. This is the corrected one. I'm gonna wait for it to open. So under here I can click Measures and D differences here. There are reasons to use D averages, but D differences is what we're gonna get out of JASP, so we're gonna stick with that. And I could calculate by typing in type 1, type 2, and some of these other statistics. Okay, so you could do that. Type, and you would have the scores. However, there's a cheat where we could do this in JASP, so you wouldn't have to open another program. You can't do this for between subjects, unfortunately. But because of the way that repeated measures data is laid out, we could use the TTest function here to calculate the effect sizes. So what I would do is click on T-Test, Paired Samples T-Test, and that's going to pop up down here at the bottom. I'm going to click neutral to positive, neutral to negative. It will help if you do it in the same order as over here. I click positive to negative. It's going to give us all 3 t-tests. Bam, bam, bam. And then what we want to do is click effect size. And that will give us Cohen's d of the difference scores here. Okay. Now your t-values are not going to match. If they do, it's kind of by chance. Because what we're doing is not correcting. So this will be uncorrected, and this is corrected. But that's really handy. That's much faster than typing it into Mode. All right, so I'm gonna copy this output. Now let's go over to our Word document here, paste that output in, and just talk about what we need from each one. Okay, so we've covered data screening, the analysis, post hocs, effect size. Let's talk a little bit about write-ups, then we'll also talk about power. Okay, here. So my results that I would write up from Mauchly's test, it's kind of all ran together, unfortunately. Let's put that here. So I could say that Mauchly's test was not significant. So Mauchly's, oops, there's no E. I always want there to be an E. Was not significant. I'm going to say P equals 0.002. Oops. 2. Computer is wildly unhappy with me right now. You could also report the W statistic if you would like. Okay. But it wasn't significant in this particular case. All right. How would I report, let's kind of run all this together, the overall omnibus ANOVA? I'd still use my F here. And silly italics. What I want to do is report the none here, since we decided it was not significant. I'm going to report this line and this line. So these two here are what we're interested in. And I'm going to do 2 and 34 equals, pull my F statistic here, 253.30. Our p-value is less than 0.001. And our eta squared and that changed font on me, which is really annoying. This whole thing is in Calibri, but I will fix that later. Equals 0.94, which you will not see in the wild very often. This is made up data, so I made it a little too perfect, if you will. So that would tell me that my overall omnibus ANOVA is significant. And that's important because that means I can now follow up with Posthoc tests to see where it's significant. Remember, when you're reporting omnibus ANOVAs, you need 3 things: F, P, and eta. So always a statistic, a p-value, and an effect size. All right, so for our Posthoc test here, we're going to make that same table we did last time. Page break here, just so we can see a little better. And then I'll just put it here. So we've got 4 by 4, I think was perfect. Except I wanted this on the next page. And let's get rid of the page break here. There we go. I think I've got it finally. So we've got group 1. Now, if you liked the format from last time because that really helped you think about what was going on, do it again. I have my research lab do this sort of thing just because it helps us think about what's happening. So our neutral conditions, we had a mean pulse rate of 87.5, okay? And the standard deviation was 16.73. Okay? So that's all like kind of an active, like I'm sitting here, I'm watching things, I'm breathing. Okay? Then we're going to compare that neutral condition to both the positive and the negative. Now I'm not putting an N, you can put an N, but N is the same. It's 18 for everybody because this is repeated measures. So it's kind of a moot point, but if you want to put in N, you can do that as well. So for our positive group here, got ahead of myself typing, there we go. The mean pulse rate is 134, so these things are really exciting. They're getting our heart rate up. These kittens and babies, that's 21.75. And don't forget, we're going to compare positive to negative as well. So let's do the negative group. The mean is 149, so we would expect that one to be the highest because it's kind of like the most shocking of all of them. So 27.75. And those are the means and standard deviations that were used in this calculation. Now, it's going to calculate the difference score as the denominator here, and there are different ways to calculate Cohen's d. So what we're going to do is make sure we tell people that we're doing d. I've always called this d diff. I've seen recently some people calling it dz because it's the traditional calculation, but I think d diff is very clear that you have the difference score on the bottom. But if somebody says dz, that's the same thing. Versus d averages, where you have the average score on the bottom. And this is our comparison column. So we're going to put in T. There's 17 degrees of freedom because it's n minus 1, okay, which we can also see down here, df. But I'm only going to use my t-test values here from the Posthoc test. So I've got negative 16.24. Okay. Our p-value, p2 key, if you will, is less than 0.001. I'm just going to fill in all of them real quick. So I'm going to save myself a little bit of time and do some cutting and pasting. Now, if you're doing this cutting and pasting, that's great, but don't forget to change the numbers. Okay, so I got negative 21.62 and then 5.38. Now, our difference Cohen's d's are 5.03. Pulling that from the very bottom down here. 3.86. Now, these are negative because of the order that we subtracted in. And if you'll give me 2 seconds, I'll have a little bit of a conversation about that. So here are all three of them. So they're all three of large effects, the biggest one being the difference between neutral and positive, although that's a little surprising given that neutral and negative actually have a larger difference score. So what's happening, right, is that the even though neutral and negative have the larger difference score, and make sure I did them all in the right order, so neutral, positive, neutral, positive, neutral to positive, it's the standard deviation of the differences on the bottom. So it might be because this is a larger error that we're getting a smaller effect. Either way, they're both really large. All three of them are very large. So we had a lot of power here, obviously, to find these differences because they're all significant. And remember, large effect sizes make it easier to find significant differences because we only have 18 people. Okay. Now, what about these negatives? Now, the negatives here match the t-values and match the direction that we're subtracting, but sometimes this is difficult to interpret, especially if you don't know which way they're subtracting. So the one reason I like making this sort of chart like this is that it makes it real clear, at least to me, what's happening. So I can see that the neutral group has a lower pulse rate than the positive group, and that's what the negative means, is that neutral is smaller. Okay. If I could have flipped this and put positive first mathematically, and all the statistics would stay the same, they just would flip signs, but the interpretation would still be that the neutral group is lower. And so having this sort of chart just helps me see which group is lower and which group is higher, because that's the ultimate goal of this analysis, is to create that interpretation. So which one's lower, which one's higher. So the neutral one is lower than both of them, and positive is lower than negative, although not as it's not as large of an effect as the other two. Right? There was something else I was going to say, now I've lost it. What you can see is all of that presented up here in our little results section here. So I have that I screened the data. Assumptions were met. I used the type of analysis here. I have my F, P, and eta here, although eta should be in italics. My post hoc correction, in this particular case, we used a two-key correction, okay, but it's still a dependent t-test. So one of the biggest things that I talk about in the overall ANOVA video is to make sure you understand the difference between the post hoc test and the post hoc correction. Two-key is not a test. This makes me crazy. Two-key is a correction on a dependent t-test. So remembering which tests are paired together. So between subjects is an independent t, repeated measures is the paired samples or dependent t. So we did dependent t-test with a correction on those, and we used two-key in our example. Okay. So neutral stimuli were found to have a lower mean than positives. So I don't include the means in here because I have a picture. Okay, we're going to make one of our own here in a second because that one's from R. And in this case, I used d-averages. So you'll see that I got very different scores because I used d-average. So here you would type in d-diff and use the numbers that we found. Okay. All right, so let's see if we can make this sort of graph in Excel. And then we'll end with power. Flipping it around here. So we talked about write-ups. Let's do graphs now. Now for graphs, it is inconsequential that it's repeated measures. So you still treat this all the same way that we did earlier. So I'm going to kind of slide this over here, this over here. We'll scroll down to, I could use this box where I've typed them all up, or our descriptives here. And you can cut and paste if you'd like. So neutral and positive and negative. See if that'll work. It's a little grumpy. This one's the means. And so I always get asked, why don't I start up here? Just because, I don't know, I don't like sticking things in this first box unless it's data sets. All right, stick these three here. Okay, so that's a little faster, depending on how well they copy. My computer's protesting having 8 things open. So we're going to highlight these, click Insert. It's a clustered column graph. And we're going to go nuts cleaning this up. So I'm going to delete this thing. I'm going to delete these bars because they don't ever print very well. We're going to just go ahead and make this gray. We're going to add axis titles, primary horizontal, primary vertical. So we've got now all of our titles on one in the graph. So I'm going to highlight the graph, click Home, and don't forget you can pause this video as you go if I'm going too fast, but this is about the 3rd time I've covered graphs, so hopefully we're all on the same page. I'll make that a bigger font and it's easier to read. Let's change these titles because neutral, positive, and negative is not descriptive enough. So stimulus type here. Here we could make this average pulse rate. Okay. Now, it does automatically start at 0, but you know, sort of this 0 to low 30s range is kind of dead. So I could cut off the bottom here with the lowest score in the data set because that would be more representative of the data. You could also start it at 0. So this kind of depends on what your people in your field do. I would personally probably cut this off in a range of data that is more realistic, given the heart rate or pulse rate here does not get this low, okay, for normal sitting human beings. Right now I'm just going to leave it, but you could change this and cut off the bottom because we're sort of squishing the graph up by including that. All right, let us now work on those error bars. So I'm going to click here, chart design, add chart element, error bars, more error bar options. 87 clicks later, we'll get there, I promise. Click custom, specify value, highlight those standard deviations once, click here twice, make sure they look the same, click OK. And that's a bit more appropriate. So this is a 1 standard deviation set of error bars, which is what I've been doing the whole time, but be sure you say that in your figure caption. So in the example right up here, the graph from R, the default is a 95% confidence interval, the way we set them up. So it says average heart rates with 95% confidence interval. Instead, I would want to, on this one, make sure it says 1 standard deviation. All right, so I'm gonna click here. I'm gonna click on the fill thing here, the little paint bucket, click line, solid, black. This is why I might tell you to use my example from the graphs lecture and just edit it, because it would be a little faster than doing this every single time, but just a reminder, so click solid here as well. And then that looks good. So this would be a more appropriate graph to use. So I'm gonna cut that bad boy, put it into Word here. I'm gonna leave this figure in here just so you can see what a different one looks like. Now, one thing I've figured out is that the formatting does not always stick when you paste into Word, because Word hates me. And so keep source formatting is where you can keep it gray. The other thing it does is it very, very helpfully adds this border around it, because you never know when you're gonna need a border. So to get rid of that, you click Chart Design, or is it Format? Oh, just kidding, it's Format. Here, click down, no outline. So annoying. There we go. That looks much nicer. The nice thing about using Word and Excel kind of together is that I actually could edit some of these features over here in Word, and they thankfully have made them match so that they are the same across both. I just find it's a little easier to edit in Excel and then paste into Word, but you can actually do a lot of this from Word as well. Okay. But FYI, if you create the graph from scratch in Excel or in Word, it will actually force you to open Excel. So it's might as well start in Excel. All right, so from here, this is where I would talk about making a figure. And I would say here, average pulse rates or heart rates, whatever, with 1 standard deviation, error bars for each stimuli type. Okay. So now, between this graph that I created in R that gives me a 95% confidence interval and this graph here that we created in Excel, I can tell that the differences in error bars are because here in this second graph I'm presenting them with 1 standard deviation, and here in this graph I'm presenting them with 2 standard errors or a confidence interval. So the one last thing that we need to cover in this video is power. So we've covered graphs, data screening, the analysis, post-hocs, effect size. We haven't talked about power. So clearly this analysis had enough power because everything was significant, right? If we believe that these are truly significant. We got big effect sizes, so probably. But if we were going to plan the study again, how many people do we really need? So let's open GPower. And then I left in this document at the very top all of the rules for power, but don't forget there's that document on Blackboard that has all of them together in one spot. So for this one, click TTest. Click on TTest to get F-test. So under test family, it's F-test. Under statistical test, it's repeated measures within factors. Okay. We're going to have to fix this effect size F, so click determine. And this time direct. Now let's type in that 0.94 we found earlier, which is very large eta squared. So calculate and transfer to main. Now look how big this F is. It gives us a very big number. Okay. But here's something new. So alpha is 0.05, power is 0.80 because beta is 0.2. This number of groups, number of measurements thing. So let's go back over here and talk about this a little bit. So what the number of groups is kind of the number of IVs. So this to me isn't totally set up perfectly for only repeated measures, because then I would just be entering the number of levels. So the number of groups here is going to be the number of IVs. So I'm going to pick 1. Number of measurements is pretty obvious. That's the number of levels. So we're going to pick 3. And then here, correlation among repeated measures. So here we can estimate this from previous research if we don't know it, and we're not estimating from a project. Or we can actually look at correlations in a pilot study and go with the smallest correlation. Or if you just aren't sure, 0.5 to 0.7 is a good estimate. Okay. So here, I left it at 0.5 in this example, but we've actually run these correlations and we knew that 0.8 actually was kind of the lowest. So let's try estimating this with 0.8. The non-sphericity correction is if you wanted to correct for heterogeneity in sphericity. And so I could put in what my greenhouse geyser or my Hunfeld were, but in general, since you're not going to know that before you estimate for sample size. And the only reason I have this 0.8 is because it's a project I've already done. So let's hit enter or click calculate if you aren't on a Mac. And so this is how ridiculous this example is. It's going to tell me that I only need 2 people because it is so ridiculously high. And that is just totally unrealistic. Even if I change the correlation back down to 5, it's still telling me I need 2 people. Okay. Now, in this example, it says we need 7. I think because I estimated the effect size as something smaller, right, as a large effect, because I didn't know what it was. So that's why I got a different number here. But let's say we don't really believe this partial eta squared is so large. And let's estimate that with like a, let's say 0.15, just for fun. So I'm going to calculate and transfer to main. This is a much more realistic number. Calculate. It says I need 11 people. So when I told you that repeated measures designs have a lot more power, a lot more bang for your buck, I think you can see that here. Because even with smaller effect sizes, even if I put partial eta squared as 0.01, which would be a very small effect, I hit calculate, I still only need 161 people. In the between subjects video, when we tested with a very small effect size, I needed 900 people. So that's the big difference between repeated measures and between subjects, other than the way you collect the data, is that repeated measures has more power. So you need less people to find the same effect size. Right. So this is how you would calculate for using GPower for repeated measures. The entire video covered data screening in Excel, the analysis, post-hoc tests, effect size for both types, how to write this up, how to make a graph, and then finally power.